Hello, everyone, and thank you for being here to follow my presentation. My name is Valentin Brunn from the University of Montpellier, France, and today I would be very happy to talk to you about a paper just submitted. This work has been done in collaboration with Alexandre Markovits, Christophe Sauty, Marco Padovani, and Christian Raab. We worked together on ionization by magnetic reconnection events in T Tauri disks. I would like to start by giving you the context of the work and showing you what kind of object we are studying. This diagram shows a young star surrounded by its accretion disk and the magnetic field line in this region. The zone of interest for our study is the interaction zone of the magnetic field line of the star and the magnetic field line of the disk. The idea is of this work is to study the particle that has been accelerated by magnetic reconnection event and that propagate along the magnetic field line and ionize the disk. The study of ionization by these particles in disks is crucial, as it's a source of heat in the disk and jets of young stars, and allows the study of periodic chemistry. Ionization is also a crucial feature for the study of accretion processes and the triggering of MRI-like instabilities. So it's all the more interesting to study the effects of non-thermal particles on the ionization rate in circumstellar disks. To compute the ionization rate we call zeta, we use the procedure of Padovani 2009. It is the integral over the energies of the product of the propagated flux of energetic particle and the ionization cross-section. To compute this, we must have the propagated flux, which depends on the column density of the disk crossed by the particles. To do this, we need to have an energetic particle injection model, J0, and a particle disk interaction model. So this is how my presentation will be structured. I will briefly show you the disk model that we use, then I will tell you about our particle injection model, and I will finish by showing you some results. The disk model that we used is computed by ProDiMo. It described the disk structure. To simplify our model, we consider only the presence of hydrogen in ionized, atomic, and molecular form, and helium. As mentioned, the flare we want to study is located in the interaction zone between the magnetic field of the disk and the star. We place it at the boundary of the disk, and we study the particles that enter the disk along the magnetic field line. The simplest description is the propagation along a vertical magnetic field line, but we wanted to have a more realistic description of a magnetic configuration. Therefore, we decided to explore the result for propagation along other magnetic configuration. We have a hyperbolic configuration in red, which describe a standard configuration, and a quartic configuration in blue, which can be explained by the fact that accretion may be more efficient above the equatorial plane, which causes this bulge. We also want to consider a toroidal component of the magnetic field. For each of these magnetic configuration, we expect the ionization to be different since particles explore different column densities. The magnetic field has an influence on the trajectory of the particles, but also on the particle acceleration efficiency of the reconnection event. So we'll now talk about our particle emission model. The spectrum of the particles injected into the disk by the flare is inspired by that of solar flares. We distinguish two contributions, a thermal contribution in dashed lines of temperature here, for example, of 1 megakelvin, which is a Maxwellian, and a non-thermal contribution resulting from the magnetic reconnection process, which is a power law. In the rest of the work, we focus on the non-thermal contribution. The power law index delta of the spectrum of a magnetic reconnection event is observed to have a wide variety of values. This variety of values is due to the diversity of astrophysical plasmas and their properties. But with the continuous slowing down approximation, we have the expression for the propagated flux of energetic particles. It depends only on the injection flux that we just saw and the loss function that can be determined experimentally and theoretically. So we have everything to compute ionization rate. To calculate the ionization rates, we integrate the product of the propagated flux and the ionization cross-section over all energies. The phi term here is used to account for ionization by secondary particle. I will finish by showing you the most important results of our paper. Here we show the ionization rate as a function of column densities, crossed for what we called our fiducial case. It is a 1 megakelvin flare that happened above the disk in the inner region at a radius of 0.1 AU from the central star, and the particle emitted propagates along a vertical magnetic field line. The injection spectrum has a power law index of 3. On the upper graph is plotted the injection spectra of the protons and primary electrons. On the lower graph, we have the ionization rate produced by each of these components and the total ionization rate in orange, which is the sum of the primary electrons and protons, and include the contribution of the secondary electrons. We see here that the dominant contribution comes from the secondary electrons. But what is very interesting here is that we have added the ionization rate produced by stellar energetic particles in red and stellar X-rays in gray, produced by a 100 megakelvin flare that is located on the star surface, which is computed by ProDiMo. And we see that our fiducial flare produces ionization rates orders of magnitude higher than the stellar flares. These results are very interesting as they suggest a potential dominant source of ionization. I would also like to show you the influence of the flare temperature on the ionization rate in the disk. The temperature of our fiducial flare has been chosen to be 1 megakelvin because it's the temperature of the weakest flare in the sample observed by Getman 2008, thus also producing the lowest ionization rate. But we also wanted to see what ionization rate could be reached by hotter flare. On the upper graph, we have plotted the injection spectra of a 1 megakelvin flare in green, a 10 megakelvin flare in orange, and a 100 megakelvin flare in blue, the strongest observed. And we plotted below the ionization rate as a function of column density by the particles shown above, keeping the same colors. We see here that the hotter flares produced higher ionization rate and that even the weakest flares are locally a dominant source of ionization compared to the stellar X-rays. In the paper, we also studied the effect of the spectral index, the flare position, and the magnetic configuration. The fact that we have found a local dominant source of ionization is very exciting, but we are aware that we overestimate our ionization rates. Indeed, the particles propagate in a very localized way around the magnetic field lines. So the ionization rate that are showed are also very localized. So to have a more realistic model, we will need a model that takes into account temporal effects that will allow us to make spatial and temporal averages. So thank you very much for your attention during this e-talk. If you are interested in further discussion or if you have any question, I will be present in Busan during the second week of the IAU in Busan. And thank you very much again, and I hope to see you soon.